So we have two Maxwell's equations left to verify, and then we know that this scenario that we're describing actually reflects a possible reality. So the two equations that we have left are, we've checked off 1 and 3. We have the even numbers left. And the first one I think we'll do first. It looks like the simplest. It's that the divergence of the magnetic field is 0. That reflects the fact that there are no monopoles. So let's see how well that works. So let's take the divergence of B. So this is, I'll label this as Maxwell's equation number 2 that we're checking out. We're hoping we get 0. Let's see. So that's going to be the x derivative of the x component of the magnetic field plus the y derivative of the y component plus the z derivative of the z component. And as we look, we see our magnetic field is directly along the z direction. It only has k hat. So therefore there is no x component, there is no y component, and the z component, we know the z component from our formula is just 1 over v times our function of x minus vt. So it's 1 over v times the function of x minus vt. Now, 1 over v, of course, is just a constant. I can pull that out of the derivative. But the main point is that nothing in here depends upon z. So the partial derivative of this expression with respect to z is, in fact, 0. And we can check off then the third of Maxwell's equations, Maxwell's equation number 2. I want to check that off. And now we're left just with this last one. Ampere's law, there's no currents involved, but we have the displacement current. So that's number 4. The curl of B had better equal mu naught epsilon naught times the derivative of the electric field. So number 4, this is the last one. And if this works, we know, in fact, that we can propagate these kinds of electromagnetic pulses and carry energy through truly empty space. So let's see here. Let's calculate the curl of B. And the question is, so I'm going to put this as a question mark, whether that will equal mu naught epsilon naught times the time derivative of the electric field. So we have two parts to this. Let's work on the curl. That's probably the more complicated of the two. So I'll put the equal sign over here, leave some space to do the curl. The curl will be I hat, j hat, k hat, the x derivative, the y derivative, z derivative. And remember now that the magnetic field is along the k hat direction. So there is, when I put in the magnetic field on the final row, there is no I hat component. There is no j hat component. And the k hat component, remember, is 1 over the velocity of the pulse v times f of x minus vt. And we have to take the, evaluate that curl, and that we're hoping will equal mu naught epsilon naught times the time derivative of the electric field. And I'll remind ourselves of what the electric field is. The electric field, recall, is my shape of the electric field that's moving, f of x minus vt. And as we said, we defined the y direction to be the direction of that electric field vector. So this here then is the electric field. Now, for the determinant. Once again, we do a cofactor expansion. Going across the top row, we would have I hat times, we cross out this row, and this column, and then I have the y derivative of f, but fortunately f doesn't depend on y, minus the z derivative of 0. So that gives me 0 minus 0. The j hat component is going to give me a minus sign. Then there's j hat. And then as I do the cofactors, I cross out this row and this column. And then I have the x derivative of 1 over vf. Ooh, that is going to give me something that's not 0. And then minus the z derivative of 0. So we have this first term to consider, x derivative of this combination. Well, there's a constant 1 over v that comes out of the derivative. So I'll have 1 over v. And then the x derivative of f, we've done that before. That gives me the derivative of f with respect to its insides. And then the derivative of the inside of f with respect to x we know is just 1. And then, of course, I still had to subtract off the z derivative of 0, which is just 0. So that's going to be minus 0. And then finally, I have the k hat part. And we're going to leave a little more room for our equality over here. For the k hat part, well, now we get lucky again because I cross out this row and this column. X derivative of 0 minus y derivative of 0. That gives me 0 minus 0. So these zeros give me nothing. These zeros give me nothing. Times 1, of course. I don't have to worry about doing that. And I've got minus 0. So it looks like I've got j hat times some derivative of f. Now, let's see what we have over here. This is interesting. It looks like I'm going to get something in the j hat direction. So this looks promising. So this has to equal mu naught epsilon naught. I'm putting my question mark here. And I take the time derivative of this product. J hat doesn't change in time. It's a constant, so I can just pull that out of the derivative. So there's going to be something times j hat. The tricky part is going to be the time derivative of f. We've done this before. The time derivative of f gives me the derivative of f with respect to its insides. So I get f prime of x minus vt. Then I have the derivative of the inside of f by the chain rule, but now with respect to time t. And when I take the derivative of this with respect to time t, because x doesn't change with t, I get just minus v. So there's a factor of minus v. And finally, let's not forget our factor of j hat. So this has gotten a little messy. Let's tidy this up and compare. So on the left, I have minus 1 over v f prime of x minus vt times j hat. On the right, I have minus v times mu naught epsilon naught times f prime of x minus vt times j hat. And are these equal? If these are equal, this pulse will propagate. And look at them. They are so close. I, of course, have a minus sign that I can cancel out. That works out. I've got j hat on both sides. I've got f on both sides. Everything lines up. This works if the speed of my pulse, 1 over v, equals v times mu naught epsilon naught. So it works if I travel at the right speed. So it looks like there are indeed some pulses. But what is the speed? This will give us some clue as to the nature of these pulses. And the speed then, if I want this equation to work out, I would multiply both sides by v to give me v squared on this side of the equation. Then I would divide both sides by mu naught epsilon naught. So the right speed then is going to be given by mu naught epsilon naught. I'm sorry. As we were saying, we get v squared on this side of the equation, and mu naught epsilon naught we're going to move on to the other side of the equation by dividing. So we'd get 1 over mu naught epsilon naught equals v squared, or that the speed of the pulse has to be the square root of 1 over epsilon naught mu naught. So that is the last key rule for how these things propagate. We definitely can propagate energy in this kind of a form. The question, though, is, what is that speed?